Okay. Chapter 17. Oh. Stick to my pattern here. And this is Chapter 17. Actually, it ought to come under the heading of spell it. This would be exam 6. Pretty sure. Yeah. Okay. So, I think we've sort of gathered an intuition about whether a reaction will proceed without any intervention. And the proper term for that is spontaneous. In other words, if you bring chemicals together, they just automatically go. Sometimes they need a little kick. And we discussed that in terms of activation energy. We've talked about kinetics already, and kinetics tells us how fast a reaction will proceed. Other characteristic that we have to be mindful of is that the rate of the reaction depends on its pathway, right? We know that in terms of when we introduce catalysts, the pathway is different because the catalyst provides a different intermediate step that allows it to run faster. It doesn't change the equilibrium, and that's where thermodynamics comes in. When we talk about thermodynamics, we're basically talking about equilibrium processes. Does the reaction go spontaneously? And that only has to do with beginning and ending. It's a state function, whereas kinetics is a path function. Okay, thermodynamics allows us to predict the direction of the reaction. Is it going to be spontaneous forward or backwards? It can't be spontaneous both directions, right? That's sort of intuitive.
So, I don't know, H2 and O will turn into water, but it will take human intervention to turn it back into H2 and O.
Yes. And O2.
And O2. Because I guess O is incredibly reactive by itself. So it'll just naturally form.
Right. It's a diatomic element. Right. So what we want to do is try to develop some procedures, some understanding of reactions that do proceed spontaneously. And that will also, the converse of that is that will tell us when they won't proceed spontaneously. So here's a little thought problem. Suppose you have, that's not really important, so many moles of gas in a, contained in a bulb at this temperature. And the bulb is connected to, by a valve to an evacuated bulb, right? So you have those two, like that with your valve, and then you have this big one here, and you have this little one here. This is the one with the gas in it. This is a vacuum. Okay. Well, might as well be consistent. 20 liter volume, and this one's 4 liters. 4 liters. and it has 2.4 moles in it. Just to check ourselves, what we're going to do is open the valve. Right? Are we going to change the number of moles of gas? No, it's the same number of moles here as when we open the valve. So what's going to happen when we open the valve? This gas is going to rush over here. Is it all going to go over here? We're going to leave some behind. Oh yeah. It'll what we normally call equalize. So the pressure will be the same throughout. Remember when we used, may have been last semester, we used Dalton's law of partial pressure to determine what the final pressure would be in a situation where you have a gas here and a gas here. You treat one separately like it was entering a vacuum and treat the other one separately like it was entering a vacuum to give you a pressure using Boyle's law. And then you add them together. Okay. So when we open this valve, that 2.4 moles of gas are going to be sucked into this vacuum over here, but not all of them. They're going to equalize. So 2.4 moles is scattered throughout. That's sort of intuitive also. In fact, you can probably hear it. So I guess now we'll have to go back to the first semester again. Right, so what are, each of these values will be what?
The change.
Right, delta H, delta E, Q, and W. Remember, this is enthalpy, which is related to Q, okay? As long as the pressure is constant, they're equal.
Yeah, I was going to say.
Which one's enthalpy? The E or the H?
This one, that's enthalpy.
And Q is like temperature, heat.
Right, this is heat. And it can be, this is the one that can be measured, Q. And we can equate Q to delta H if the pressure is constant. And that's usually what we do to gain access to these values.
Then W is what? Work.
Work, right. In fact, this is where I want to start. Work is force through a distance. Right? If you apply a force over a distance, you have work. Right? That's the physical definition of it. So, has any work been done?
And the particles have moved to the other container.
Right. But has any work been done? No, the gas has moved, but it hadn't pushed on anything.
So it's not just movement, it is.
Can you extract any? Work is a measure of what can you do with the energy that makes it useful, right? Like a piston moving. Right? If a piston had moved in this process, then we could extract some work from it. But in this case, there's nothing
like
done.
if opening the valve had pushed something, like pushed a valve. Like
Well, yeah, that
internal.
aside from the fact that we turned the valve, right?
But like if there was something else in there that movement of pressure moved something.
Right. Say if we had a piston here like this,
Right.
and we could measure the force, and as it moves through a distance, we get some work out of it. But in this case, no. The temperature is also constant at 32 degrees. Right? If the temperature is constant, heat's constant. We can't measure any heat without a temperature change, which means that one's constant either. That one is 0, that one's 0. And these are related. They're not equal to each other, but they're related. And they're actually all 0.
And E, I'm sorry, is
Energy.
Is energy, right? Whereas these are heat. So energy can be, it's all inclusive, all forms. The whole purpose of this exercise is not to flog these terms again, but just to emphasize the fact that if all of these are 0, how do we account for the fact that the gas moved from here to here? There's no driving force that we can assign to each one of these. Right? So what is the driving force?
Pressure. Like,
I thought it was just how gases behave.
they want to seek to fill up the space.
Right. That would be in terms of a law. What we're trying to do now is trying to explain why.
Why do they seek to fill up the space?
Yeah, why do they seek to fill up that space? Okay.
Question.
That's the $64,000 question. So we invented a term. It's called entropy. Entropy is what drives this reaction, or this movement of gas. Now, the oversimplified version of entropy is randomness. And it's useful. I mean, to understand this as an increase in randomness from squeezed here to unsqueezed here, you know, that's one way, but it limits its usefulness if we only think of it in terms of simple positional randomness.
I was going to say, but the different things generally tend towards disorder.
Yes, that's true. That's true. But we're going to refine our definition so we can use it under wider circumstances. Okay, so this is what has happened. Right. The difference between these two images, notice, is that these molecules are more widely spaced. They have more room.
So less chance of change in their, is that where we're going with this?
They have more elbow room, right?
Less chance of running into each other, colliding, and doing something else.
Right. I was hoping I'd get to the, okay, it's coming. So the driving force for a spontaneous process is an increase in entropy. Now we have to define our terms here because the authors and most chemistry books refer to, and the term for entropy is S. Only we cannot measure S directly. We can only measure, it's kind of like heat. You can only measure a change. And, actually, I misspoke. You can't even measure entropy.
I was going to say, I'm literally trying to imagine quantifying disorder.
Yeah, you cannot measure it. It is a calculated term. So you have to measure some other things and determine entropy as a product of mathematics. But assuming we can.
I know what you meant by, like, so it's something someone's already computed at some point and it's a known number?
No, well, I'll show you how to calculate it.
But it's something that's been calculated and we
Yes.
use it in
equations. There are tables, right?
To help derive other measurements.
There are reference tables with entropy values, but those values weren't even directly measured. They were calculated from others that could be measured. Okay, and that'll come. So the convention is if the delta S is greater than 0, then there's an increase in entropy. And if delta S is less than 0 or a negative number, there's a decrease in entropy.
So entropy is disorder.
Right, we're using that definition for now. We're going to modify it in just a few minutes. But for now, that's fine. So as opposed to, see, because what was our, if we say this, that means with our system and our surroundings, that means heat's going in, right? If it's negative, heat's going out, right?
And the thermic, exothermic.
I'm sorry?
Endothermic,
Yes.
exothermic.
Right, endothermic, exothermic. That's the convention for delta H. But for delta S, if disorder is increasing, it's positive. And negative, it would be decrease. That's just so we know what our conventions are. Okay, here's the more widely applicable definition of entropy. It has to do with probabilities, right? It's statistical. So if the entropy is increasing, we are giving the particles in the system more possible arrangements. We call those microstates. So if we give those particles more elbow room, they have the ability to occupy many more different unique microstates. And for that definition, every particle is unique. In other words, if you have an oxygen and a nitrogen, and an oxygen and a nitrogen, having this oxygen and that nitrogen over here rather than here is not the same as these two being over there. They're unique. Okay, I'm going to give you an example.
Microstates are unique, each like in a unique state.
Unique arrangements. Yes. So what we do is we calculate the probability. We don't really. This is a thought problem. So when I say calculate in parentheses, I mean quotes, we calculate the number of possible microstates for the particles in the system. Well, it's very large, yes. Not infinite, but very large. So that's why for the example, we're going to simplify our microstates, a number of particles, down to just 4. Right, that's in the next slide.
That's a more understandable number.
There you go. So here we have 4 particles, A, B, C, and D. And one possible microstate is for all of them to be over here on this side. Okay? So there's only one possibility for that. There's only one possibility for all of them to be on the other side. Right? But if you just put one of them on the other side, you can put an A over here, or you can put a B or a C, or that gives you 4 possible microstates for the arrangement of 3 on one side and 1 on the other. Okay? If we have 2 on either side, then the number of microstates goes up to 6 rather than 4. And if we have 3 on the right and 1 on the left, again, you have only 4 possible microstates for that. So the most probable arrangement for these particles is this one, where you have 2 on one side and 2 on the other. That's the most probable.
Right, because there's 6 options.
Right.
So just
That's the most probable number of microstates for this system. Now, of course, if you have Avogadro's number of particles, then the calculations go up
6 out of what,
geometrically.
16?
I'm sorry?
And 6 out of 16 options. 16 total, 6 out of.
Yes. So probability would be 6 divided by 16. Right.
You said the word probability. I have a sneaking suspicion you were delving into physics, probability, and statistics. It's not happening. I was like, this is a little bit of statistics and a little bit of physics. And I'm like, this is just great.
I feel the same. I feel you.
So we have common misery here.
Yeah. Co-misery.
Okay. So in general, we divide the discussion of entropy into two types. One, we can reference to our example of particles having their microstates. And for that one, we call it positional probability or positional entropy. It just depends on where they are. Okay. And if we use that reasoning, then we find that as a substance changes state from solid to liquid to gas, we find that the number of microstates is greater for the liquid than the solid, and the gas greater than the liquid. So the entropy is increasing from left to right here. Okay, that's fairly easy to grasp, I think.
Mm-hmm.
So let's see, let's take some examples. What would be the delta S? Oh, by the way, conventions. We haven't used them yet, but I think it's important to get these definitions in now so that they'll have a chance to rattle around while we're doing these problems. When we say delta S, we can go back to our system surroundings. Now, the authors often equate surroundings with universe. But I like to draw a distinction between immediate surroundings and the entire universe. Right? And the way I do that is, if we're talking about the universe, then this part is open as far as the eye can see. Then we can say universe. But if I want to isolate my system and surroundings, so I'm going to have an isolated system. Remember what that is? Energy can't cross the barrier, matter can't cross the barrier. That's an isolated system. Then I say surroundings is this part, system is this part, and total is my universe.
No energy or, would you say it can cross?
No matter or energy for isolated. There are three types of system definitions. You can have an open, matter and energy can cross the barrier, no problem. You can have closed. No matter crosses the barrier, but energy can cross. And then isolated, where neither one of them can cross the barrier. So when we run our calorimeter experiment, we're trying to simulate as close as possible an isolated system with our styrofoam cups. Okay, so back to my definitions. So you can have delta S for a system, right? What's happening inside here. And we also say just delta S with no subscript. Right? If you see this with none of that, that's what it means. So these are synonymous in this class.
Like an isolated system, you're saying? That delta S?
No, actually anytime. Anytime we say delta S for the system, we could also say delta S with no subscripts, and we mean system. If it has no subscript, we mean system.
You mean isolated system?
No, because energy can't cross this barrier. This is the isolated part.
Oh, okay.
This would be more like closed. Okay, because energy can cross that barrier, but it can't cross this one. See, the only reason I'm isolating this is so that I can call it total rather than universe. Okay, and then you can have surroundings. And under special conditions, when we don't isolate the system, then I would say universe. And then, of course, you can have total. And total is just the summation of the entropy of the system plus the entropy of the surroundings. Okay? I'm gonna leave those up there while we talk about this other stuff. Okay, so when we say delta S here, no subscripts, that's for the system. What's happening in the system. So predict the sign. Is delta S increasing, which means positive, or is it negative? The evaporation of alcohol.
Increasing?
Increasing, definitely. How about freezing of water?
Decreasing.
It should be decreasing, right? Because it's becoming more ordered. Compress an ideal gas at constant temperature.
Decreasing.
It should be decreasing, yes. Fewer microstates. Heating an ideal gas at constant pressure. Now, increasing, yes, that is true.
Because, I mean, even though it's constant pressure, if you heat it, it's going to make more movement.
More random motion, right.
Yeah.
So that increases the microstates as
So
well.
even if it's at the same pressure, yeah, just more happening.
And it didn't say anything about the volume, so we have to assume the volume is constant too. So if we heat it, pressure is going to increase, right? Because of
But since the pressure is constant, then the volume had to have changed.
right. If we increase the temperature, then the pressure has to increase. If we keep the volume and the moles constant, then one has to increase as the other one does to give us a constant. And dissolving sodium chloride in water.
Increase.
Right, that would increase. And in that case, we're really only concerned with sodium chloride. Okay. So, we've been talking about here the second law of thermodynamics, which just means there are several ways to express this law. One way is to say delta S for the universe is always increasing. And when we say universe here, we mean the entire universe. Right? So that means for everything that we know exists out there, entropy is always increasing. So then that begs the question, how do we get delta S for our system to go backwards, to be less?
By isolating the system.
I'm sorry?
By isolating the system.
That's part of the reason. We have to couple one system with another one, or do something out here that will cause the entropy in here to decrease. Right? You have to force it. If this is the natural order of things, then you have to force it to go backwards in a local area or a local volume of space. Okay? Because its natural tendency is to be positive. So for those situations where we had
So that's today's deep thought. The universe is positively disordered.
yeah.
That's our take home. That's my gold nugget.
So when we say freezing of water, it's not normal for water to freeze. So we have to couple it with another process that we allow to go spontaneously. And in the process, it removes heat from our water to freeze it. Right? So air conditioners, refrigerators, and freezers, that's not spontaneous. We have to add energy and drive that reaction backwards in order to make the water freeze. That's basically my point. Okay, so if we want to determine, one way to determine whether a reaction is going to be spontaneous, we look at the summation of the delta S for the system and the delta S for the surroundings. And if it's positive, the total then will be spontaneous. So this is my preferred arrangement.
So can I rephrase what you just said and see if
Sure.
I caught it?
Okay.
So if you just said if you contain and isolate the system, then to allow what happens on the inside of it to find out whether or not it's spontaneous. Is that what you said?
Isolate both of them together.
Right.
Right. Because what we're going to do is add the entropy of each one together. But actually, I like this one better. Add the entropy of this one with the entropy of that one. And if the summation is, the total is positive, then this isolated whole will produce a spontaneous process. Okay. So I apologize because these slides flip back and forth between total and universe. In fact, they prefer universe because they were produced by the authors. So just as we're talking universe, you can think in terms of the whole universe, but I prefer to think of it as total. Because, I mean.
So when they're saying universe, they're meaning your box right there.
Yeah.
So not really the universe, but a controlled, isolated box around the system
Right.
we're studying.
When we say this right here, we do mean the universe.
Right.
But when we say that, we're talking about total.
Well, that's only a little confusing.
That's not, I mean, thermodynamics is confusing enough on its own. We don't need any help.
Right.
Okay. So if we have a positive delta S for the total, then we should have a spontaneous process. If it's negative, then the process is not spontaneous in that direction, but in the reverse direction, it is spontaneous. And then here's a good one. If the summation is 0, our isolated setup here is at equilibrium. There's no drive to go either direction if the delta S is 0. It does happen, right? I think of any chemical reaction that we've studied in.
Think about being in bed in the morning. 0 drive, right?
Right.
Sorry, Mr. I'm trying, people. I'm trying.
Okay. So let's look at this theoretical. If we have a substance that's liquid and it's we have an equilibrium process. I don't know if it's equilibrium yet, but it could be with its solid.
Wait, so the same molecule in 2 different states? Is that what
Yes.
you're saying? Okay.
Yes. It's just a change of state.
Okay.
Which direction involves an increase in energy randomness or positional randomness? And there, I've only alluded to. We've talked about positional randomness and a little bit of energy randomness when we were heating the substance
Well,
and getting an increase in entropy.
the positional randomness, from what I understand, based on everything you've said so far, I would say is to the left here, in the liquid.
Yes.
And
Yes.
energy randomness, wouldn't that also be to the left?
Energy randomness, well, it requires energy input to go this direction, right? You have to put energy into a solid to make it a liquid.
Right.
So to the right should be exothermic. So we would think that the exothermic process to the right would be preferable. So this process is exothermic from left to right. And the energy randomness favors the formation of the solid. But that's not the whole story. Positional randomness, yes, it prefers the liquid because we've increased the number of microstates. But if we add energy to this, then adding energy to it makes it to the left is favorable. Excuse me. No, formation of the solid. Let's see. Exothermic in the past generally means the preferred direction. Why? Because systems prefer to be at the lowest possible energy that they can find, which means they have to give up energy. As it turns out, there's like a running battle going on between positional and energy randomness, positional and energy entropy. And it depends on whether the temperature is high or low as to which one wins. So which takes precedence? As temperature increases, the positional randomness is dominant. So at high temperatures, with positional randomness dominating, the release of energy becomes less important. So a good way to think of that is, if we're starting from a really high temperature, then to go from one state to the other, we give up less energy. In other words, less important. I don't know if I'm explaining that very well. Probably not.
Can you give an example that would illustrate that?
How about trying, rather than melting ice, let's melt salt. And it takes several thousand degrees temperature to melt salt. At that point, you're already at the high temperature. The more important process then is the ability of the ions to move past one another. In other words, their position is more effective at the higher temperature. It's more predicting at the higher temperature than the temperature is. Because at that high temperature, what will 1 degree change mean? Almost nothing. Whereas if you're with water at 100 degrees, 1 degree change means a whole lot more on a percentage basis. As the temperature decreases, energy randomness is favored and positional randomness becomes less important at low temperature. It may require that we just accept it as gospel at this point. So, the takeaway from all this confusion, this mental randomness, is that there is a temperature at which there's a balance between energy and positional randomness. And that temperature, in this case, is the melting point. A phase change is that temperature at which energy randomness and positional randomness meet. So let's see, let's try, maybe we can derive some solace from these questions. So if a reaction is exothermic and becomes more positionally random, so the exothermic we said earlier was preferred, and positionally random is more preferred for its increase in microstates. So under those conditions, that reaction we could predict is spontaneous because both driving forces are favorable. Exothermic is favorable, positionally random is favorable. That's spontaneous. If it's exothermic but becomes less positionally random, that is, goes from, I guess in our example, less positionally random goes from liquid to a solid, but it's still exothermic, then the only way we could say it's spontaneous is if the exothermic exceeds the value of the positional entropy. And the converse of that is endothermic becomes more positionally random. Then the only way we could say that that's spontaneous is if the positional randomness exceeds the value for the endothermic. So this is the middle ground where you really can't tell until you have the values to compare. But if it's endothermic and becomes less random, then we know that that's not spontaneous in the forward direction. Yep.
I don't want to interrupt, but what time do we need to start now? Do we have?
Oh, we're skipping it today.
We're skipping one?
Yeah, we have to.
Where does that put us? Does that change the schedule?
It just means we move that lab
To
1 week. Yeah.
We'll just be back where it's supposed to be.
and then there'll be a 2-week gap between that and the final lab. And the final lab is just a fun exercise.
Today, we're gonna have fun. I'm looking forward to that.
Yeah. We're gonna build a battery.
Okay,
basically.
so just real quick, so I understand. So today we were going to do lab 5, but now we're gonna do lab 5 next Monday. Is that true?
That's the one with formation constant. Oh, wait a minute. I'm in the wrong place.
So we're gonna do lab 5 on Monday, April 15th.
Yes. Yeah, that one moves to the 15th. That gives us a break of the 22nd before lab 6 was on the 29th.
Okay. Okay, great. I was just starting to feel nervous, like we're not gonna have enough time for lab. We're not.
Yeah, I should have. That slipped my mind.
Okay. I'll relax now.
Okay. So let's see. If we focus on the surroundings now, and the delta S that's associated with the surroundings. The entropy of the surroundings actually depends on the direction that the heat flows. Because if heat is flowing out of our system, that increases the energy entropy of the surroundings. So this would be positive as heat flows out. So on an exothermic process, we would expect delta S surroundings to increase. Exothermic, excuse me, exothermic.
Where heat is disappearing into the system.
Right, it's leaving the system and entering the surroundings. That should increase the entropy of the surroundings. The energy
You
entropy.
said exothermic, I got it backwards.
Right, okay, so that's true. And vice versa. If heat flows this direction, then the delta S for the surroundings should decrease for an endothermic process. So what are we saying? Well, when heat flows, temperature has to change. Right? So the delta S for the surroundings is linked to a change in temperature. It's dependent upon temperature. Okay. So what's the long and the short of this is that the delta S for the surroundings is directly proportional to the heat transferred, right? But since a change in entropy is more greatly affected when you start, let's see, if your entropy is lower, back up. It does depend on temperature, right? And it also depends on the heat transfer. Now they're related, but they're not equal. They're factors that we incorporate into the expression of delta S surroundings. So if the surroundings are starting at low entropy, so we start at low entropy out here. This is hypothetical. We start at low entropy, then the effect of that transfer of heat is greater than it would be if we are already at high entropy, right, on a percentage basis. Does that make sense? If we start at low entropy, then you add heat to it, the effect is greater than if you are starting at high entropy and you add the same amount of heat. Okay. So we've got to consider heat and temperature, and here we have the quantity of heat, and there's the temperature, because the entropy is directly proportional to the amount of heat transferred. But, excuse me, yes, this goes up, that goes up, and inversely proportional to the temperature. Because if the temperature is low, then this will be high. And the way to get that is to put temperature in the denominator. So the long and the short is, delta S for the surroundings is proportional to the enthalpy and inversely proportional to the temperature. And that previous slide showed us why that negative sign is there. And I think we can reason that out. If delta H is positive, it goes this way, right? If we're saying delta H is positive, then what happens to the entropy? The entropy has to go down. And in order for it to go down and remain consistent with the convention, we have to put that negative sign there, right? Because if this is positive and that's supposed to be going negative, we got to stick that negative there. And what would happen if we're going the other direction? Then it would be negative. But that would increase the entropy of the surroundings. And in order to increase the entropy of the surroundings, if this is negative, then we have that negative there to make the whole thing positive. And that maintains our convention. Of course, temperature won't have any effect on the sign because it's absolute, right?
So adding let me just rephrase this. Adding energy to the system decreases the entropy of the surroundings.
Right.
So, what if the temperature was 0?
Then you have the third law of thermodynamics.
Which is,
The entropy of a perfect crystal at absolute zero is 0.
because you change by.
You said a perfect crystal?
Yes,
Is that what it would take?
that's the definition.
Say it again, for what?
The entropy of a perfect crystal at absolute zero is 0.
I guess anything at absolute 0 would be a crystal, wouldn't it? Give you gas.
Well, that means it's in an equilibrium.
Yeah, there must be a reason for saying
Let's say it's got to be some reason, because I thought that absolute 0 was the temperature at which an ideal gas turned into a liquid.
No, it's the temperature at which an ideal gas would disappear. Remember?
Sure.
Remember,
Something
So
about
if
it.
the entropy is 0, that means it's just in an equilibrium state. It doesn't want to do anything. Right? Is that what you said?
that's true, but in this special case, it's related to the fact that T is also 0. So if we say, well, this is for the surroundings, right? You're talking about the entropy of the system.
Oh, okay. So the entropy of the surroundings of a perfect crystal? Is that what we're saying?
Well, I'm the wrong person to ask that question. Yeah, sorry.
Okay. What is
You need a physical chemist to answer that one.
What's a perfect crystal? Like, what's an example of a perfect crystal?
I would start with an ionic solid and then cool it down to absolute 0.
So
Right.
actually,
Because there's always a possibility that even though you're at absolute 0, your substance could be amorphous. In other words, not a perfect crystal.
What is the numerical value of what's the label on absolute 0? Is that in
0K?
it's in Kelvin?
Yeah. Mhm. Well, there are other systems, but they're always at 0, whatever they are. What my point was that temperature doesn't have any effect on the sign because it starts from 0 and it's always positive.
Okay, so we're always going to use Kelvin.
Yes, we're going to stick with Kelvin. So if we go to the, actually this should have that, I'm going to use total. Oh, there it is over there. So with these two, let me shrink this a little bit, plus delta S surroundings. There we go. So if both of these are positive, if a change in the system entropy and the change in the surroundings entropy are positive, then this is automatically positive, which means spontaneous. If these are both negative, then this one's negative and it's non-spontaneous. Those are two situations where we can definitely say spontaneous versus non-spontaneous.
So it's the entropy of the system plus the entropy is positive and the entropy of the surroundings is positive, then the total is positive and it's spontaneous.
Yes. Now for the other situations where you have, so you could have a negative here, positive there, or positive here and a negative there. It depends on the magnitude, right? If this one is larger than that one, then it'll be positive. If this one is smaller than that one, then it'll be negative. And if this one is larger than that one, it'll be positive. And if this one is smaller than that one, it'll be negative. So under those circumstances, you can't tell without the actual numbers.
Okay, where you just threw me off was how can you pointed at,
If this is bigger than that one,
how would it be bigger? Like, I guess the positive negative sign's confusing me because the positive numbers.
well, if you say this one's 8 and this one's 4, the difference is +4, right? So that would be spontaneous.
Okay, so we're just showing the less than, greater than, not a positive or a negative number.
Right. But if this one's 4 and that one's 8, this would be -4. And it'd be non-spontaneous. Okay. So it depends on the magnitude at that point. If one's positive and the other is negative, you have to have the values to tell you whether it's spontaneous or not. Now, after going to all that trouble, we've got a better way of dealing with it. It's the concept of free energy. And it was developed by Josiah Willard Gibbs. That's why they call it G for Gibbs free energy. And Gibbs was working on the concept, trying to come to terms with when you undergo a process, whether it's physical or chemical, when a system undergoes a process, how much useful work can you get out of it? What's the maximum amount that you can get from a process? Well, as it turns out, delta H is the potential energy for doing work, the enthalpy of the reaction. But
Potential energy for doing work.
the potential energy of the reaction, which could be, from which work could be extracted. How much is not available for work is this term right here, T delta S.
So you said T delta S is how much we can't.
Right, that's lost. And delta G, the difference of these two, is the maximum amount of useful work that can be obtained from a reaction. Now, if you look at the units of measure, what did we say for delta S for the surroundings equals minus delta H over T? Well, no, that's not fair. Let's not go there yet. Sorry. Because this is the system, right? That delta S has no subscript, so it is the system. We're talking about the system. But that's, this is the maximum amount of work that you can get from a reaction that has this enthalpy. So if we can minimize this value over here, then we can maximize this one.
Is the and T is temperature?
Yes, and it's Kelvin.
So
The smaller we can make this value here,
in the delta H, the change in energy
it's enthalpy.
or enthalpy, that's measured in joules.
Yes.
And is there a label for entropy when we're calculating this?
It will be joules per K.
So joules minus Kelvin
That one. And this one's K.
times joules per K.
So that one cancels, leaves us with joules.
entropy is measured in joules per Kelvin.
Yes.
So. So we were just left with joules, a measurement of joules
Yes.
for the change of free energy.
Enthalpy and free energy. If we're prorating it, so to speak, in terms of moles, then every one of them will have moles in it also, like joules per mole. Right, so that doesn't affect the overall because we've divided the whole thing through by mole. So that's another possible unit that you may encounter.
But just don't get hung on it.
Right. Focus on the joules.
Spoken like a pirate ship captain.
That's Captain Jack Sparrow.
It's funny, I was thinking earlier, I don't know what we were talking about, but there was a quote from Pirates of the Caribbean that popped in my head. It's more than imagining that helpful.
He had a way with words. Okay, so the delta S for the universe at constant temperature and pressure is equal to negative delta G over T. Which you have to accept. So this is total or universe, either one, is negative delta G divided by T. So when, now that we have this expression, when is the reaction spontaneous? It's spontaneous when delta G is negative. Because if it's negative, that makes this positive, that makes that positive. So a negative delta G equals or yields spontaneous. Whereas positive delta S for total is spontaneous. A negative delta G is spontaneous. And I like to think of it this way. If you have a system here, and we use the convention, so the free energy, we're extracting free energy from the system, and that's doing work for us. So the negative delta G extracted from the system means that it's spontaneous.
Negative G is when energy has been extracted from the system.
To do work, yes. So the maximum amount of work that you can get from the system in any process is delta G. Now, of course, that's theoretical. You can never actually get 100% delta G out of a system. There are always some losses. Even if you account for the change in entropy subtracted from delta H, there are going to be other losses in there as a practical matter, such as heat leakage. Yeah. You really don't have an isolated system. Okay, so if a liquid is vaporized at its boiling point, now I have to add some conditions here. If this liquid is vaporized at its boiling point, we're going to assume that we're able to extract work from it. In other words, the piston can move.
Like steam.
Huh?
Like steam.
Yeah. So liquid is vaporized at its boiling point. If it's happening at its boiling point, then we're at an equilibrium state. But we do get work out of it, right? Because when you vaporize it, you're building pressure.
I would have assumed that would be negative. Because there is work.
Well, work is the same convention as heat. So negative means we're extracting work from the system. So when gas does work on its surroundings by expanding in this engine, we're extracting work from it, which means it's negative. And in order to do that, we add heat to the system by heating it. Right? So we've got a positive Q. And let's see. Well, it doesn't say constant pressure, but even if it's not constant pressure, the enthalpy will also be positive. Now, if we do have constant pressure, they're equal. But they're proportional to one another, whether it's positive or not. I mean, whether pressure is constant or not. The change in system entropy is positive because we're going from a liquid to a gas in this process. Surroundings, of course, would have to be negative entropy.
Why is that?
If we are increasing the entropy of the system, then the surroundings has to decrease in entropy. Well, under these circumstances. And that's in terms of energy, right? Because we're
putting it into the
we're putting
water.
energy into it, and the energy's got to come from somewhere. It's coming from the surroundings. And then delta G, because this is boiling, delta G is 0.
Why?
Yeah, explain my answers here. Any boiling point system is at equilibrium, which means
Same with melting, going from solid to liquid and liquid to
yes.
vapor.
Yes.
So melting point and boiling points is melting point also a 0
Yes. Right.
for delta G?
Right. That's one of the reasons understanding, let's say, temperature and progress, right, as we heat the solid up, reach its melting point, then the temperature stays constant until all the solid's gone. And then the temperature increases as we heat the liquid. And then when the liquid starts boiling, temperature stays the same until it's all gone. Then we can heat the gas. So that's, at this point right in here, delta G is 0. Let's see, let me go back. Let's see. Where's delta G? Okay, if we multiply this times T, then we get delta G. Temperature is not changing. Temperature change. Well, no, that's not a good explanation. Forget that. So if we know that delta G is 0 in an equilibrium situation, then this equation becomes that. And when it becomes that, then we can take this one and put it on that side, right? So the sign becomes positive. So under those circumstances, the enthalpy of the reaction is equal to temperature times the entropy of the system. Then 30. 12:20. I think we can finish. Okay. So if the enthalpy of vaporization of a substance is 45.7 kilojoules per mole, and its normal boiling point is 72.5 degrees centigrade, calculate each one of these: delta S for the system, delta S for surroundings, and delta G for the vaporization of 1 mole at that temperature. All right. So at the boiling point, we've already accepted, haven't explained it very well, but we've accepted that delta G is 0. Right? So if delta G is 0, and the surroundings are delta minus delta H over T, we had that equation earlier, right? Surroundings equals minus delta H over T. So we can calculate the delta S for surroundings at minus 132 joules per K. I probably should have dropped that mole out of here because it says for 1 mole. Substance, calculate for 1 mole of the substance. So it's really minus 132 joules per K. Then at equilibrium, we know that the total entropy is 0. So if the total entropy is 0, then we add these two together. That means that the system has to be equal to the surroundings, but opposite in sign. Right? So the delta S for the system at this equilibrium process has to be the same here. Oops. So you're going to start on its own or not? No. All right. One of those glitches. Okay, so let's take Gibbs' equation and look at various conditions. If this is positive and that's negative, so if this is positive and this is negative, that means this term is negative, and that means delta G is negative. Right? So under these circumstances, this whole expression is negative. That's always spontaneous. It doesn't matter what T is, because T is positive. All temperatures under these circumstances where delta H is negative, exothermic, and delta S for the system is positive, under those conditions, delta G is negative always. So when delta S is positive and delta H is negative, we are spontaneous everywhere and always. Yeah.
So negative delta G is spontaneous.
Yes. Negative delta G is always spontaneous. Let's go to the bottom of the chart and get that one out of the way. What if delta S is negative? Right? So if it's negative, then, and delta H is positive or endothermic, then this expression becomes positive because of the negative sign. And this one becomes positive. So under those conditions, at any temperature, the reaction is non-spontaneous. Okay, this one is spontaneous always. This one is non-spontaneous always. In that direction, in the forward direction. In the reverse direction, it would be spontaneous.
What do you mean in forward and the reverse direction?
Well, for the process, if you were going from here to here, we're saying that these conditions say that it's not spontaneous that direction. But in the reverse, it is spontaneous. Right? Because what's happening? In the reverse direction, you're actually getting these conditions. These conditions become those in the opposite direction.
I guess maybe when we have a problem with an example, I'll maybe understand that a little bit better.
Yeah. You need
So we're reversing a chemical
that's an example.
reaction.
Mm-hmm. Just like your hydrogen-oxygen reaction to make water. It would be these conditions, let's see, definitely ectothermic, and delta S, well, definitely, right, because you're generating a lot of heat. So for the forward direction for our hydrogen-oxygen to make water this way, hydrogen-oxygen from water is this one. Not spontaneous, but in the other direction, it is spontaneous.
Never happened in nature.
The reverse, no, except perhaps in a lightning strike. Then you're coupling it with another process that adds energy and drives it the other direction. Oops. There we go. Now, for the other two, they're conditional. So if delta H is negative and delta S is negative, under what circumstances would this be positive? Well, that's going to be negative, right? So it would make it positive for this term, but it depends on the magnitude. This is only positive if this term is greater than that term. So that means T has to be large. If T is large. So high temperature under these conditions would give you a spontaneous reaction. Where delta S is negative, it's decreasing.
Wait, it says spontaneous at low temperature.
Oh, excuse me. Let's see, did I get that wrong? Oh, I went to this one. Spontaneous at low temperature, we're exothermic. Wait just a minute. H negative. Delta S is negative. I think that's wrong. I mean, just look at the numbers. Oh, shit. I'm wrong. Spontaneous has to be negative. That has to be negative. So T is small. Right? If this term is very small, then that one dominates. Yes, small temperature. Low temperature. And for the other one, in order for it to be spontaneous, this one's positive. This one is, wait a minute. I got that wrong. Negative, negative. There, that one's positive. there we go. For negative, negative, small temperature. For positive, positive. Yeah, for positive, positive, this one's negative. So the large temperature for this one would overwhelm this one and make it
Right.
negative. Right. So if temperature is large for that situation, then you get a spontaneous reaction.
Well, what's considered a high temperature for these kinds of things?
400 or 500 degrees centigrade. Low temperature would be like, negative 100. Because this is relative to absolute.
So,
Right.
but we're doing everything in Kelvin, so.
Right. Room temperature would be 298 K. That might be considered large. And it all depends on the reaction, right? These are relative terms. So the actual values here determine what is large and small for T. Let's see, a gas reacts with gas A, reacts with gas B to form AB at constant temperature and pressure. The bond energy of A and B is much greater than that of either reactant. So what does that mean? I have to draw a picture. So we got this one plus this one yields this one. So the bond between these two is, the bond energy here is greater than the bond energy of here, like this and like this. So the bond energy here is greater than for either one of these. So that means, and what the bond energy means is that with a stronger bond, it takes more energy input to break that bond than it does here. Right? So we have to add more energy to this one to break it. That means this is exothermic. You're getting heat out because this is a stronger bond than these two. Okay, so that's my picture. So the sign is going to be, for an exothermic reaction then, delta H would have to be negative. Right? How about the sign of the surround? Let's see. Surroundings is a little more difficult to deal with system. There's surroundings. Here we go. If delta H is negative, then delta S for the surroundings is positive because of this formula. Right? Negative delta H over T. So we know delta H is negative. That means delta S surroundings has to be positive. How about delta S for the system? We don't know for sure. We have to assume that the delta S for the system is roughly 0. We really can't tell. But the universe, we add them together, and of course, the universe is going to be positive. This is the tricky one right here. We don't know what the delta S for the system is.
Why is that?
I knew you were going to ask that question.
Sorry.
Let me see if I can figure it out.
So it's
Delta S for the system is,
so this was endothermic or exothermic?
exothermic.
This is exothermic.
Yes, exothermic.
we're releasing heat.
Yes.
But the delta H is a negative.
Right, because heat's leaving the system. It's a negative. I can give you a good explanation for that.
Okay, that's okay. I can forgive you.
So here's our third law of thermodynamics. The entropy of a perfect crystal at 0 K is 0. So the entropy of a substance increases with temperature. In other words, relative to absolute 0, all entropies are positive. Right? If you're starting from absolute 0, then you can only go up. Okay, how about practical applications? We alluded to this in the beginning. You can find these values, and these are standard entropies.
When there's the degree sign, is that what you're saying?
Yes, for that little 0, standard conditions for 298 K, which is 25 degrees centigrade, and 1 atmosphere pressure. So this is the entropy that they acquire when they rise from 0 K to 298 K. Right? So what that means is, remember delta H's, it's possible to have 0 delta H, right, for a compound. Well, actually, all elements in their standard states have a delta H of 0. Right? But every substance, element, compound, doesn't matter what it is, they always have a delta S, a standard delta S, because we're going from 0 to 298. Right? So they all have, because the third law says the only place that there's 0 is at absolute 0. Right? So their delta S everywhere else is a positive value. So if we want to find the delta S for the reaction, we use that similar type of calculation where we take the delta S's for the products and subtract the delta S's for the reactants. And that's the delta S overall for the reaction. Okay?
So,
yeah.
I'll just wait. Maybe you'll explain.
If we were given enthalpy values here, that one would be 0, and this one would be 0. But these are entropy values, so they all have positive values. Okay? So if we have products minus reactants, then if the entropy of the product, all the products combined, is greater than the entropy of the reactants, then we have a positive entropy for that reaction. In this case, we don't. We have a negative entropy.
So these values for these standard entropies are just already calculated for us and will be a given.
Oh, yes.
And so I like simple math, so this is simple. We're adding up and when we do it in this example, okay, so it's calculated for water, it's calculated for sodium hydroxide, it's molecule.
Right, so you would have to multiply this one times 2.
Yeah, that's guess where I'm
Well,
going.
let's start here, products minus reactants. So 2 sodium hydroxide would be 100.
Right.
Plus 1 of these would be 231. And then we subtract 2 waters, 140, and 2 sodiums. 102. So that gives us our negative 11 joule. For that reaction.
Mhm.
Okay. We can do the same thing with free energies. We also have those values calculated in tables. Right? So up to this point, up to this chapter, we've only worked with these values, but there are standard values for these and standard values for those. And like any equation, if you know these and these, you can find that one. Or if you know this one and that one, you can find that one. It's like any, there's one unknown. Or if you know this one, well, this one, and this one, the T, since these are standard, that T is always going to be 298, isn't it? Under these standard conditions, with the little zeros, standard temperature is 298 K. So let's see if we can do this. A stable diatomic molecule spontaneously forms from its atoms.
I'm going to predict G is negative because we said it was spontaneous right off the bat.
Good test-taking technique. Yes.
That means that
Delta S. Or you could do delta H, either one. So when you go from individual atoms, let's see, just make up one, let's say here. So you have 2 oxygen atoms yield O2. When you form a bond, what happens? Gives up energy, doesn't it? So this one should be negative.
so then that would mean the entropy is positive. No? Oh, you
Well,
put it up there.
Right, well, let's look at this one. If that's negative, this is negative. And T is 298, right? So it's negative that. So this one, that one, it's negative, that one's negative. This whole term has to be negative. Well, no, it doesn't have to be negative. Could be small positive. Okay. Delta S is negative because you're going from 2 moles to 1 mole. It's more ordered. Right? That's why this one is negative. Okay, no problem. I would expect the entropy for this one from 3 moles to 2 moles to be negative.
Right, because we're decreasing disorder, so we're
Oh, I forgot, I have an explanation. Right, so here, this was the kicker right here. 2 atoms to 1 molecule is a decrease in disorder. Okay, how about the following system? Let's see if we can make sense of this one. PCl3 plus Cl2 yields PCl5, and the delta G is minus 92.5 at 25 degrees. what will happen to the ratio of partial pressures of PCl5 to the partial pressure of PCl3 if the temperature is raised. These are all gases, by the way. Put that in there. And the delta G is equal to negative 92.5. So the ratio of PCl5 to PCl3, PCl5 to PCl3 ratio, what happens to that? If temperature is increased. This is negative.
Decrease.
If, let's see, delta G is negative, we definitely know that.
So,
But the, let's see, temperature would be increased from 25 to whatever. So if we increase the temperature, that's a positive change. Well, that doesn't matter actually, because it's always positive. There we go. So delta S, I'll let that part out. Delta S is going from 2 moles to 1 mole. So delta S decreases during the reaction. Is delta H
so delta S,
negative?
you said decreases?
Right. Delta S is negative. Right. So if we put negative in here, we get a positive. But this is negative. So this one has to be more negative than that one. So delta H is negative. This one's negative because of that.
But the change of enthalpy has to be a greater number.
Than this one combined.
Right.
Yeah. So we're increasing the temperature. If we increase the temperature, oh, okay. So now that we know that this one is negative from all this other information that we've gleaned, this one's negative. That puts delta H on this side as a product. And if we increase the temperature, that increases this one, drives the reaction back that way. So that's why now this ratio will decrease if we increase the temperature. If we had determined that delta H was positive, it would go on this side, and increasing temperature would produce more product. But the key is finding out what's the sign of delta H. That's the trick. So we go back just to reiterate. Delta S would be negative because we're going from 2 moles to 1 mole. So that's negative. And if we increase this value here, that makes it more positive. Change the positive. But still, that has to be negative to make that negative if this is positive. So that tells us that delta H is exothermic, which means it's over here. Then we can draw our conclusion from that. Okay. Okay. So these values, particularly the delta G, can give us some valuable information. This equation, you just have to accept it. The delta G under present conditions is related to the delta G under standard conditions by adding this term. That's if you know the pressure of the system.
That's the natural log.
Yes, natural log.
Is that the same R value as before, like that we have from?
This is the one that has joules in it. Is that
8.3145.
Yes, right. That's the one with joules in it. Also, we can say that the delta G under these conditions is related to the standard delta G if the system is not at equilibrium. In other words, if we can calculate Q, then we can find out what delta G is relative to the delta G for the standard conditions. We just need to know the Q. So what that means is if Q is actually equal to K, wait a minute, I'm skipping ahead. All right, what does the actual delta G mean for the chemical reaction? Well, the reaction may not go to completion, and this talks back, this refers to equilibrium. You know, under equilibrium conditions, we have calculated where the reaction is. Does it favor products or reactants, right? And the delta G tells us that it's not going to necessarily go all the way to completion, although that does happen sometimes. But it will go to a minimum energy level. It'll fit in that trough. That's the way I like to think of the production of explosives, right? They store a lot of energy in the explosive, but it's not the reaction that goes to completion, because otherwise you wouldn't have any energy stored in it. So it finds a local minimum, and that's what this refers to. A local minimum energy, and now it's stable, as long as you don't add enough energy to get it past that other point. So that's what you do with an explosive, particularly if it's shock sensitive, like nitroglycerin. You know, if you got a vial of nitroglycerin, you drop it on the floor, and that's the end of you. So the equilibrium point occurs at the lowest value of free energy available, a local minimum. So this delta G would then be 0 under the given conditions. Now that's to draw a distinction between delta G and delta G0. These are defined conditions at 1 atmosphere, 25 degrees centigrade. Okay. So under these conditions, if we're at equilibrium, then our delta G equals to 0, and then that's equal to this plus that. And at equilibrium, the value is K, not Q. Okay? So that gives us a tool for determining K. Or if we know K, we can determine delta G under standard conditions. Right? Because now if we solve for delta G0 and we're at equilibrium conditions, then delta G0 is equal to RT log, natural log K. Okay? And we've been able to determine the equilibrium constant fairly easily in the lab. And we can use that information to tell us what delta G0 is, rather than having to measure delta G.
So the big K, that's our equilibrium constant.
Yes, right, that's what K is. Okay, so if this is equal to, if the delta G0 though is also equal to 0, what does that say about K? This is 0, then K should be equal to 1. Why? Because log base E for natural log of K is equal to what value? Let's just say X. E to the X is equal to K. Right. So under what circumstances would this value be equal to 0? Right? If this is 0, then that value has to be 0 because these are positive values. So that one has to be 0. So e to the 0 is equal to 1, right? Any number to the 0 power is 1. So that means K has to be equal to 1 under these conditions, right? If delta G0 is equal to 0, then K is 1. And by that same reasoning, if delta G0 is negative, then K has to be positive. And if delta G is positive, K has to be negative. Okay? Let's see. Let me see if I put that in here. Or if you have to memorize that. I don't see it. So you have to know that one. All
I
right.
have to know what one.
The relationship of K to delta G. Delta G is 0. All right. So let's go back to the original impulse for Gibbs to develop this equation. He wanted to know how much energy could be extracted from a process to give you the maximum amount of useful work. So that's why this maximum work, is equal to delta G. Delta G is the actual maximum amount of energy that can be converted to work. And I'll say it again, that's hypothetical. Any real pathway wastes energy. It's inevitable. All you can do, well, it's good information to know. If you know the maximum amount of work you can get out of it, then you know if you're getting close. So you improve the efficiency of your engines because you know what the maximum amount is possible, and then you can increase the percentage of conversion. Generally speaking, the Frenchman Sadi Carnot came up with the heat engine efficiency equation. So we can calculate how efficient, what's the maximum efficiency you can get from your automobile engine or from a steam engine or any kind of heat engine. Let's see, I can remember what it is. I think it's maximum efficiency for a heat engine is 1 over T squared minus, not squared, 2 minus 1 over T1. So really all you have to be concerned with is the difference in temperature. So that's why they say the more efficient engine is the one that runs hotter. So the difference in temperature between the engine and the heat sink, or the atmosphere, is the real key to efficiency. Right, so those little bitty engines that they're putting in cars now, they run hot. They're really hot. And that's for their efficiency. So they're even down to like cars with 3-cylinder engines. Yeah. Motorcycles have always been taking advantage of that, like 1-cylinder engine. I think the most I ever had on a motorcycle was 2-cylinder. Okay. The other concept with efficiency has to do with the idea of reversibility. Can the process be reversed? And the maximum work that you can get out of a process depends upon the process being reversible. Now, every process in reality is irreversible. But if you shrink the time interval down small enough, you could theoretically be reversible at that very small interval. And that's what they do. And that's what the theoretical delta G, or W max, is derived from. The fact that under certain circumstances, under conditions, theoretical conditions, you can make a process reversible. But since they're not reversible, since all natural processes are irreversible, you lose efficiency there. All right, here's the common language for the laws of thermodynamics. Right? The first law, you can't win. You can only break even. In other words, you can't get more energy out of the system than you put in. Right? So that puts the kiboshes on perpetual motion machines. Second law says you can't even break even. That's because of entropy. You lose something in entropy. Any transfer of energy will result in some waste, unless you could achieve a temperature of absolute zero. Right? If we could achieve absolute zero, then that efficiency for Sadi Carnot would be 100%. And then the third law, you can't even get out of the game. In other words, you can never achieve absolute zero. It's a physical impossibility. Now, I don't know if I've mentioned it before, but there are some laboratories that claim they've reached absolute zero, but they do it 1 molecule at a time. In other words, they find a laser beam, a frequency of laser that will be absorbed perfectly by a molecule. And they catch the molecule coming this way and fire a laser beam at it, it stops it. No motion, absolute zero. Technicality. But from a thermodynamic perspective, you can never reach absolute zero, because there's no heat sink lower than that to which you can extract energy and put it over there. So those are the 3 laws of thermodynamics.
They read like grim life universals. Like, I mean, you can't win, you can't break even, you can't get out of the game.
Right, there you go. And all of this together just means that every time we use energy, we degrade its usefulness. So the universe started way up here in useful energy, and it's going to end up way down there eventually.
So really, we just shouldn't feel bad about it, because it's inevitable.
Yeah.
All energy's wasted.
Just use it.
Just accept it, people.
Do the best you can on your way down. Okay, next time we'll do, look at the review and do our lab.
So is our lab report due next week?
Yeah, next week. If you need the time.
And then for the test, you said just go through and redo.
Right. Redo them all and, redo the ones that you missed. Yeah, show me your work and then I'll give you credit for them.